All right, so this morning we're going to be learning a little bit about data structures. Now, like I said before, there's really a lot to know. This is a very deep topic. We are going to be just barely scratching the surface of this, so you kind of know, what the subject is about, why it's important. So before we get too deep into this, for those of you who don't know at all what a data structure is, I should probably define it so you know what we're talking about. So I would say that generally in computer science, a data structure is a data organization, management, and storage format that enables efficient access and modification of that data. So another way to think about this is a data structure is a collection of values, the relationships between them, and functions or operations that can be performed on them. Great. So there are a handful of different data structures.
Word wrap? Sorry, can you word wrap?
I think it's on.
Oh, okay, I just saw it go to the end.
Yeah, this line ends like right here. Yeah, okay. So there's a few different data structures. I mean, there's a lot of them. The ones that we might talk about today will be arrays, which is the very most basic kind of data structure. A lot of more complex data structures are built on top of arrays, such as queues and stacks, which are really just special types of arrays, potentially special types of arrays. So we have a linked list, which is another list-like structure. It's kind of like an array. Talk about hash tables. I'm going to show you a little bit of those. And then there's various types of trees. I'm going to talk very, very briefly about different types of trees. Probably going to talk most about hash tables today. But before I talk about any of the specifics of these data structures, you must be wondering, like, why does this matter? What's the point? More specifically, why is there more than one data structure? Why don't we just stick everything into an array? So the most concise way that I can answer this question of why is there more than one data structure is because different data structures can perform different operations at different speeds. So depending on what type of operations you need to perform, like maybe you're adding lots of data or you need to search very frequently, depending on what operations you need to prioritize, you might choose one data structure over another because it makes things that you need to do commonly easier. So it's hard to say, generally speaking, what the best data structure is. Some are generally more popular than others, but it always depends on your use case and what you need to accomplish. So maybe to give you like kind of a trivial example of this, just for something to think about. So this is just going to be pseudocode here. I'm not even going to execute this. So we got this array in JavaScript. So let me ask you, if I want to just add one item to this array, how many things about this array need to change?
Depends if you add it to the beginning or end, right?
Yeah, I'll let you choose which end you're adding it to.
If it's the beginning, then everything has to change.
So just for a little visual clarity here, I've added the indices to the array. So that's totally right. If I add something to the beginning of the array, then I have to make one change for every element in the array because I have to change the index for all these other elements. But there's a simpler way. So what if I want to just add an element to the end of the array? Like that's much simpler, right? We just have a new element, and then this is going to be 6. So it's a relatively small change. And moreover, adding one element to the end of the array is just as easy to do no matter how many elements we already have. But so let's say we need to search this array. So using the index of method in JavaScript, how difficult this is depends on how big the array is. Because this array isn't sorted at all, G could be anywhere in it. So the number of checks that we have to make is potentially the same number as the size of the array. So here with this unsorted array of letters, adding things is very easy. Searching things is a little bit harder. But now let's imagine a slightly different example. We had an array of sorted letters. So let's say here, I need a way to add a new letter to this array, but it's a sorted array, so I need to keep it sorted afterwards. Well, sorting takes time, and it takes more time depending on how big the array is. So we can see here to keep the array sorted, adding new data is harder than if the array is unsorted. However, for searching, searching a sorted list is easier than searching an unsorted list. Like if I'm looking for, the letter T, I don't have to check every letter. I just go to the middle and say like, okay, is T before or after M? It's after M. So I'm gonna, look at this half of the list and then go to the middle and say, oh, I found T, great. So by sorting the list, I can search it much more efficiently than if it was unsorted. And we're gonna get more into the specifics of that, those differences and how to describe it tomorrow when we cover Big O. But really before we get too deep into anything and the specifics of all these different data structures, I just want to explain that, in my opinion, this is really the crux of data structures. This is why we care about it, because different operations can be performed at different speeds by different data structures. So like in this example, if we need to prioritize adding things really quickly, but we don't need to search very often, I would prefer unsorted data. But if searching is very important to be done quickly, but we don't add new data as often, then I would prefer a sorted data structure. So depending on your use case, you're going to choose one data structure over another. So before we get into some of the specifics here, I'm going to show us some visualizations. I just want to leave you all with an inspirational quote. So this is a quote from Linus Torvalds. He's the inventor of the Linux operating system. And he's also kind of a notorious jerk. And I just always love hearing him say who he thinks are bad programmers. They say that he's become a lot kinder in more recent years, but he still has kind of that reputation. And this, I do think this is a very important, meaningful quote. I didn't really understand it for a long time, but I kept coming back to it, and I feel like it's becoming more clear to me as I'm getting more experienced. Because now I try to keep my code as simple as possible. I don't do any very clever things with my logic when I can avoid it, but I try to, use the right data so that the rest of the code is easier to write. All right, so let's look at some actual specific data structures here. So I found this really neat website. It's hosted by some university, I don't know, but they have some visualizations of different data structures. So here we're actually looking at a couple things at once. Don't worry about the stack bit. We are looking at an array. So an array in computer science is the most basic data structure available. This is different from a JavaScript array. They have the same name, which is a little confusing. But so an array in computer science is supposed to be just like a list of memory locations on your computer, like physically, that they are all adjacent to each other. So in this diagram here, all these sequential boxes, each box is supposed to be like one slot in memory where you can store like one bit of data. I'm not really a hardware expert, so this metaphor might get a little strained. But you're supposed to imagine this as being like taking up physical space in your computer. And importantly, all of the elements of the array are physically next to each other on your machine. So we call this a contiguous data structure because all of the data is physically next to each other on the machine where it's stored. A contiguous data structure. All the data is next to each other physically on your machine. So that also means that arrays have a fixed size. So here, this is specifically a 30 element array. It can hold exactly 30 things in it. And if you try to push more stuff into it, it's full. That doesn't work. So here I'm going to just push in the number 10 and kind of visualizes, okay, great. So the 10 goes into that first spot. We can add another item, goes into that second spot. It shouldn't be too terribly interesting to you. It's just a list of data, kind of similar to the arrays in JavaScript, similar to lists in Python, except that this is actually how the data is stored, like physically on your machine. So they're really easy for searching. Like if you know where the start of the array is, it's at this location 0, if it's a 30 element array that, location 10 is the 10th element in, and you can just increment the index to search through them. So they're really good for searching really quickly or jumping to a specific index if you know which index you need. But they are just very simple, very basic. You can't do so much with them by themselves, but we will see that there are some more advanced data structures that are built off of arrays. So let's take a look now at another really fundamental data structure. I feel like these are kind of the two most basic data structures that people will talk about, people ask you about. Second one is the linked list. So you should notice right off the bat, a big difference is that the screen is empty here. So the linked list starts out as empty. We'll just put in a 10. And now it has a single node. And then as needed, when we add new nodes, they are created, but they're not actually adjacent to each other in the computer's memory. They could be stored anywhere on the computer in your physical memory, because each node of your linked list has actually two pieces of information. There's the data itself, this 25, And then there's also a reference to the next element in the linked list. So this is a non-contiguous data structure. Each element can be anywhere physically in memory, because each element has a reference to the next. So in like your homework tonight, for example, you're going to have to write code to essentially create a linked list like this, just some list of nodes that are connected to other nodes in a chain. And you'll have to, search internet, add items, delete things. Just, the basic operations you do to any data structure, adding and removing data, updating it, searching it. You're going to have to do it for these different data structures. So that's kind of part of why I'm not showing you too much code today, because if I showed you any code, it would basically be just doing your homework for you. So I'm trying to tell you the concepts theoretically and help you visualize these so that you'll be able to do the homework assignments. All right, so great. I'm adding more elements to my linked list, connected one after another. Another distinction, there are two types of linked lists. A singly linked list is where each parent node has a reference to its child, or each previous node has a reference to the next. And maybe you can guess what a doubly linked list is, where each node has a reference to both the previous and the next node. So it's not really hugely different whether it's singly linked or doubly linked. A doubly linked list is going to take up more space because you're saving more data. You have two references instead of one for each node, but it's also more flexible because you can traverse it forwards and backwards. Whereas, for a singly linked list, you can only traverse it in one direction. So depending on whether you need that flexibility, you might choose one of these over the other. But also using either kind of linked list is going to be more considerate of your storage space. Because like we saw here, I have, this 3-element linked list. And then so it's only using 3 elements to represent that. And there's so much white space on my screen. But when I was using the array, it starts out with 30 empty elements. And so, I can fill these up one at a time. But no matter how many of the array elements are actually used, it still takes up the same amount of space on my computer. So generally, there's some logic to that internally. Like an array might start out small, and then if you try to add too much data to it, like if I tried to add an index 30 and it only has 0 to 29, what is common a lot of computers do is they create a new array that is twice the size of the original array, and then copy all the original data into the first half of that new array. So then you've still got the second half as empty. So periodically, as you're pushing into an array, you're going to have to resize it. I mean, computers do that automatically nowadays. That's not something that we're going to be thinking about, but it's an implementation detail that you should be aware of. Somebody might be happy that you know this at some point in your future. So yeah, those are arrays and linked lists. I want to show real quick a stack and a queue. So a stack and a queue, those are both more advanced kind of data structures that you can build them with arrays or with a linked list. So, and I believe we've mentioned this before, but I'm just going to write it down so we're all on the same page. Stack is an array or a linked list, any list-like structure, where you can only add or remove to one end of it. So commonly adding to the array is called pushing. So as I'm putting all these numbers on, they're going in the higher numbered indices. And then if I want to pop, I don't even get to pass in a number here. It just takes off whatever's in the highest numbered index and then removes that from the array. So this is a stack implemented with an array. We can only add and remove from the highest index that's filled. Similarly, we can implement a stack with a linked list. So as I'm adding, they only go to the end of this list. And if I pop, it'll only remove the most recently added item. So, 1, 2, 3. Yeah, okay, then it removes 3, 2, 1. Just the geometry kind of threw me off for a second. All right, so a queue, very similar to a stack. So queues and stacks are just more limited, really, than a regular array or linked list. But because we know that there's only one way to interact with them, they can be useful for various purposes. So like you could use a queue to model like a literal queue. If you have people waiting to be served by customer service representatives, every time somebody tries to contact support, you put them in a queue. And then whenever a customer service representative is available, they just grab the top person in the queue. They don't have to worry about who specifically they're going to work with, just grab the top off the queue. And that guarantees that people are served in the order that they started waiting, which is fair for waiting for customer service.
So is it grabbing from the top or the bottom? Since the stack is grabbing from the top, right? The queue's the opposite. Is it like first in, first out for a queue?
Yeah, so we say the stack is, yeah, first in, last out, whereas the queue is first in, first out. Whether you think of one thing as the top or the bottom is kind of relative. It's all a matter of perspective. I mean, stack, I guess you always kind of think about it as a perfect way because of like the gravity metaphor. You wouldn't remove plates from the bottom just by turning it upside down. Anyways, so the next thing I want to talk about, well, I'm sorry, actually, do people have any questions just about what we've covered so far about arrays, stacks, linked lists? I know this is going really fast. No? Okay. So let's talk a little bit about hash tables. Has anyone heard these before? Can anyone just like tell me off the top of their head what a hash table is? Nobody? That's cool. So a hash table, conceptually, you can think about these as being pretty similar to like dictionaries in Python. A hash table allows you to create a list of key value pairs. And after creating a pair, you can retrieve that value using the key. So this is great because this is very fast. You don't have to like iterate through a whole table, like a whole array in order to find a particular value. If you know the key, you can go directly to it. So no matter how big your hash table is, it should take you the same amount of time to find a particular value for a particular key. But under the hood, hash tables are often implemented using arrays. Okay, but so in a second, I would like to show you a really quick demonstration of a hash table just in code. But first, we should talk briefly about what hashing is, because this is kind of a core thing that a hash table does. Can anyone tell me what hashing is?
When you hash a password, you use an algorithm to take the password and basically encode it into something else, like a different combination of maybe numbers and letters.
Okay, yeah. So hashing is used to transform a value into another value. It is commonly used for password security, and we're going to cover that in some detail later on in the course when we're dealing with authentication. But for right now, what we need to know is that hashing is something you do with a function. We say a hashing function takes some value as input, returns a hash. Today, our hashes are going to be integers, but more commonly, the hash would be a very long string. So when we get to passwords, the hashes are going to be like alphanumeric strings with symbols in them, maybe 40 characters long. Also, very, very crucial, hashing is a one-way operation. So hashing value is very fast. But there is no way to reverse a hash. At least there's no straightforward, honest way to reverse a hash. The ability to reverse a hash is called cracking, and that is not covered in this bootcamp. So let's see. Also very important, hashing the same input always produces the same output with no randomness. So that's very critical. Our hashing function needs to be reliable every time. And also interesting to know, it is possible, but unlikely, that multiple values will have the same hash. This is known as a hash collision. You'll see in this demo how this becomes a problem, but I am not going to build a sophisticated enough hash table that it actually solves this problem. Okay, so let's, just to help us kind of visualize a hash table, because this is, I think, a more complex data structure, but also very fundamental. I'd like to, show you some code. Just kind of one way you might implement a hash table using arrays and objects and other data structures that are available to us in JavaScript. Create a class for this. Let's have a constructor. I chose to do this in JavaScript for no particular reason. So for starters, I said that the actual data for a hash table under the hood is stored in an array. So internally, we're going to create this array and we're going to pre-fill it to the size that we think is big enough. So I'm going to say this is a 64 element array. That's going to be the data table that we're using internally. So I'm going to call that this.table. So it is a long array, 64 elements, but they're all empty. They're all undefined. Now, the hash table needs to know how it's hashing values. So, given a key, we need to turn that into a number, and that number is going to be an index in our array. So we're going to pass in some key, like name or age would be, keys that we might have in a hash table, like we've had those in our dictionaries. And this function needs to somehow transform that key into a number, but it needs to do it reliably, so it gets the same value every time. And it has to be between 0 and 64. So this is one very naive way to do that. This is not like a production-ready hashing function, but this is a very simple hashing function that I think just conveys the point, conveys what we're trying to achieve. All right, so I'm looping through all of the letters in the key. So it's going to be some short string like name, age, or password or whatever. And then for each of those, I'm getting the character code for that key and then adding it to this number, the hash. So we haven't seen this before. It's not super important, but basically for every letter of the alphabet, there is a numerical representation for that letter. It has a character code. So I'm just getting a numerical representation of all of these numbers and then summing them up in the hash. So any given set of letters, I should be able to add them up to the same number every time I calculate the hash. The problem though is that this is going to potentially give me very big numbers. They might be bigger than 64, which is the length of my array. So before I return the hash, I'm going to mod it. So this guarantees that this hash value that I produce, this number, is somewhere inside of this table. Justin?
When it comes to predefining the size of the array for the hash, it's, did you say it would be contiguous in this case, right? It's still an array. I guess it's just arbitrary. I'll just ask the question. For a contiguous array that you have to define the length of, how, I recognize that each element of the array would be stored physically next to each other in the memory, but how does it know the max size of what an element could be?
Like what you can store in a single element of the array?
Yeah, if it's reserving physical space in the memory, is it also reserving a specific?
I imagine, I don't know, this is actually beyond my experience and understanding, so I probably shouldn't be making guesses. Adam,
That's
I don't know
fair.
if you have any thoughts on this.
Is this specific to JavaScript arrays?
Yeah.
Shouldn't be, just, low-level computer science. How is an array stored on your computer? How does your computer know how much data can be in one element of the array?
That's a good question. Arrays, so like a real array data structure, I believe has to be of the same type, which is part of the answer to that question, because it won't be storing like strings and integers and objects like class object instances. So my guess is that it then depends on like the programming language and specifics and stuff, because I'm thinking back to like Java, and I could create an array of like instances of a class, of a particular class. And my guess is that Java like figures out how much space is needed for each element of the array. I'll Google this too.
I can do the
But-
research. Just
But
curious.
yeah, I think it's going to depend. Like in the C programming language, it might be done differently than in Java. And in JavaScript, arrays are not real arrays. So they're actually objects that behave a lot like Python lists and like arrays, but there's like, it's not contiguous in memory. Like a JavaScript array is not actually an array data structure, though for our purposes, it works just the same.
Okay, no worries.
Sorry, that was a lot.
Yeah, great question. Just sorry, I don't have the low-level knowledge required to really answer that confidently. But also, Adam raised a great point that JavaScript arrays are not the same as these kind of low-level computer science arrays, and just generally, the data structures we use, like in our actual programming languages, the lists and dictionaries, are going to be more high-level, more sophisticated than these kinds of classic data structures I'm teaching about. You're never going to have to deal with a hash collision using a Python dictionary. Python can figure that out for you automatically. Whereas in this implementation here, it's like really easy for two keys to end up with the same hash. And like, I just don't handle it. It would just overwrite data. All right, so continuing onwards. So now we know how to hash a value. So if we want to set a value, so add something to this hash table, set So first we hash the key, and that tells us the index in our table where we can put this value. And then we put the value in the table at that index. Simple enough. And then when we want to get the item out of our hash table, we just need the key. And we can convert that key into an index again, using our hash function. And then just index into our underlying array and return the value there. So like I was saying, this is a very simple, naive implementation of a hash table. It doesn't even acknowledge hash collisions at all, which I'm going to leave that as an exercise to the viewers about how we would address that. But this should show you kind of the basics of what it does. We take in a key, convert that into some numerical representation based on the letters, and then use that as an index for our array, put the data there. So that in the future, if we want to get, age or whatever key, we don't have to search through the entire table to find the data we're looking for. We just hash the key, which is much faster than searching through the table. And then that tells us directly where our desired value is. So that's the big part of the importance of hash tables, is just the speed that no matter how large the hash table is, you can find any value immediately, in one operation, given that you know where it's at, or you know the key for it, sorry. And so we're gonna talk about that in more depth tomorrow as we get to big O notation. That's how we mathematically describe how much faster certain operations are than other operations. But that's getting a little bit too deep for today.
I did a little Googling, Raphael, on that. Great question. But I don't know if we really want to circle back to it now, because I know that there's probably some other stuff.
Not really, honestly. There were a couple other tidbits. I have like 2 sentences to say about trees. I don't really want to get deep into them, just let you know that they exist, basically.
The short answer to the question is, with like arrays at like the lower level that Raphael was talking about, and I needed to be refreshed on this, we're dealing with primitive types like strings, ints, chars, and at that level, like the system knows how much space to allocate for a string or for an integer, depending on like the programming language. And when you declare an array, you have to declare its type and its size. And so that's how it determines how big an element is. It's based on however, like 8 bytes for, I don't know, an integer or a char, right? And so then if I declare an array of characters, each element that in that array will have a size of 8 bytes because it can only hold characters. I hope that made sense.
Sounds about right.
Angel, I saw you had a question.
Yes, Raphael, can you run an example of like the hashing and then retrieving it and stuff like that?
Like, so this should totally work. Excuse me. Oh, that's okay. Cool. So I set age, set name, I get age, tells me 24. Similarly, I can get name, returns Alice. I could probably put some more logging in here if you want to see the internals of it, but does that help? Does that show you what you're looking for?
Yeah, it does. I just want to see how what it would return, and then
Yeah, I mean, it should work familiarly to like how dictionaries work. You
Yeah.
just add,
but the dictionary values are all like saved within your computer, so you don't look. That's like all the hashing. All that does is kind of save everything in Unicode, and then it stores it there until you call your function to get it.
so the hashing just lets you find an index for where in the array the data is located. So the hash doesn't like transform the value, it transforms the key just so we can turn the key into a location for the value. If that makes sense.
Okay. Yeah, that helps. Thank you.
All right, so just some quick final notes, just talking about trees. There's a whole bunch of different types of trees, and I'm not going to get into the specifics of them, but generally speaking, a tree is a data structure that has some root node, and I don't know, there's data in it, whatever. And then it has child nodes. Can I just copy paste this? Sweet. So yeah, it's gonna have child nodes. Then those children can have their own children. Etc. Okay, cool. So that's a tree. But that's not super interesting by itself. What you're going to find a little bit more commonly are binary trees, which is a tree in which every node has at most 2 children. So now this would be a binary tree. Our root node has 2 children. This guy has 2 children. This guy has none, but that's fine. He could even have 1 child. That's also a valid binary tree, as long as he has no more than 2 children for any of these nodes. So there are other kinds of trees. You could have like a trinary tree, I guess, where every child has 3 children of its own. And so then there is a subtype then of a binary tree. This is actually something that I think people ask questions about a little more commonly. A binary search tree is a binary tree that is sorted. So for every node, for example, it'll have the smaller item on the left and the larger item on the right. So when you're implementing like a binary search tree, the nodes would actually be named like left and right. You probably wouldn't just have an array of nodes because they're very different. You know, the left one is the big one, the right one is the small one, or whatever. So in this case, let's say we're saying left is big, right is small. So 5, 9 is bigger than 6. Wait. I guess this whole tree needs to be kind of reorganized. So we could put like 4 over there. I guess I'd have to rearrange more things here to make this a valid binary search tree. But yeah, generally the rule is like larger things on one side, smaller things on the other side. Maybe there's good visualization of that over here. We have a binary search tree. I'm going to insert 8. So it's just the first node, it's 8, great. And if I insert 7, smaller than 8, so that goes to the right. Let's insert 99. So that's bigger than 8, so that goes to the right. 11. So that's bigger than 8 and smaller than 99. So we go right and then left. We add 12. That's again bigger than 8, smaller than 99. Bigger than 11. So it goes there. So we add 40. We add 101. So this one's actually bigger than 99. So that's going to go to the right. So yeah, it's easier to see when I'm doing it dynamically as I'm like adding elements to an empty binary search tree. You can see how it's like sorting them into the right order. But because of this structure, that small things are on the left, big things are on the right, it makes it really easy to search this tree. So if we were looking for a specific number, like, find the number 12, for example, you don't have to search every node in this tree. I could start at the top and we say like, okay, I'm looking for 12. That's bigger than 8. So let's go to the right. And then I'm at 99. Okay, well, 12 is smaller than 99. So let's go to the left. I'm at 11. 12 is bigger than 11. So we'll go to the right, which is the only option. But then that gets me to this 12. And we didn't even have to look at, this 7, 101, or 40. So binary search trees are good because they're useful for searching things. It's right in the name. All right.
Are there any like built-in search methods that automatically use a binary search tree, stuff like that? Or is everything just doing like the normal, like iterating through each item of it?
That's a good question. Because I know that the built-in like search methods should be pretty efficient, but still like searching can be more efficient if your data is sorted. And I'm not sure if the built-in search methods in Python or JavaScript will assume sorted data or can take advantage of sorted data in any way. So it's possible that if you have data that is sorted and you need to search through it faster than what the normal search method does, and like you've sorted it for the purpose of quick searching, you might have to write your own binary search algorithm or some kind of optimized searching algorithm if it's like taking advantage of specific structures of your data. But I've not done that.
Yeah, I think like Python and JavaScript, they're built-in searching things use algorithms that don't depend on sorted data. But like all like databases, search engines, everything uses binary trees under the hood for all sorts of stuff where it's like more complex or it's like something that's sorting data. They're just everywhere.
Yeah, for sure. So you actually just remind me of something. There's one last type of tree that I want to show. This is by far the most complicated thing I've mentioned today, and I'm basically just going to scratch the surface of it. Basically just to say that there is a data structure called a btree. This is not a binary tree. The B does not stand for binary. I don't remember offhand what it is, but my point is just that these are different. Don't get them confused or like you'll sound like you don't know what you're talking about. Maybe if I add some more.
I might have gotten them confused. Is this what databases use, Raphael?
This is. So if if you take this course and what you decide is that you hate front end, you hate back end, all you like are databases, and you become like a DBA as your main career path, you will probably become very well acquainted with B trees and exactly what this data structure is. So I know it's a type of tree, but see here. So here, it's not a binary tree. It's saying each node can have at most 3 children. And there's some relationship between these children and the parents that makes it slightly more efficient than a binary search tree. It's because we're putting like more children per parent, it doesn't get quite as deep quite as quickly. And so for some reason, having a data structure that's not quite as deep is just a little bit easier to work with compared with like a binary tree. It can get very deep as you add lots of data to it.
Yeah, I'm actually looking it up on Wikipedia. It says that it maintains sorted data like the binary tree, but allows for, like you said, nodes with more than 2 children.
I also want to show just kind of a fun little tidbit here. I'm making a binary search tree. I'm going to insert some data into it, but specifically I'm inserting all of the data in sequential order. So what are people noticing about my binary search tree? Does this kind of look like a different data structure?
Like a linked list?
Yeah. So this is just kind of like a funny tidbit. is that depending on the order that you insert the data into a binary search tree, and if you don't like rebalance it, so you could, like resort the search tree after you add to it. But if you don't do it, you just naively add data one after another, what you actually get is a linked list. And so we'll cover this more tomorrow when we talk about algorithmic complexity and how different data structures are better or worse for certain purposes. And it also matters if you're talking about best case scenario or worst case scenario. And what you're going to see is that in many cases, a binary search tree is much better than a linked list. Like in the typical case or in the best case, binary search tree is going to be faster than a linked list for lots of things. But in the worst case scenario, they're going to perform exactly the same, because in the worst case scenario, a binary tree is a linked list. So I think just seeing that like this makes that easiest to understand. But I just think that's kind of funny. All right, so on that note, that is everything I have to tell you about data structures for this morning. I've got a little bit of homework on this. I'm going to actually write some code to implement these data structures that I've just been talking about and showing you. But other than that, do we have any questions about this afternoon? Oh, and I need to generate pair programming partners for all of you as well. Yeah, so what questions do we have? No questions. Awesome.
So for, I'm sorry, Rafael.
Go for
So
it.
for deciding what data structure to use, it kind of just depends on what problem you're trying to solve.
Yeah. Just imagine, you're storing lots of data and like, okay, we need to save lots of data very frequently, but we don't actually need to like search it as often. So imagine if like I own a trucking company and we have GPS trackers in all the trucks, and every second it is sending their GPS coordinates into a database. And then maybe like once a week or whatever, I want to do some analysis to see like how, who is moving the fastest, who's moving the slowest, who is, shipping the most cargo or whatever, who is spending too much time at Wendy's, that kind of stuff. So in that situation, it would be really important that we can add to our data structure as quickly as possible. But I'm less concerned about being able to search through it as fast, because I said that I'm going to just do that once a week. And that's a job that can probably run like at night, even, while I'm not watching my computer. Whereas on the flip side, if you're doing, what is it? Some kind of like predictive text, imagine like an autocomplete. So, you type 3 words like STA, and your computer can guess that you're trying to type star. So for something like that, you might have a database of all these different word prefixes, and then like ways that those prefixes can be finished with complete words. And because this needs to work while someone's typing in real time, it is absolutely essential that you can search that data structure as fast as possible. But since you're probably going to be building that data structure offline before any of your users are even exposed to it, it doesn't need to be as fast to insert into that data structure. You can like take a few minutes or hours even or whatever, inserting all those word prefixes for your autocomplete database, as long as you can retrieve them as fast as possible. Does that make sense?
Yeah, it is. Thank you.
Cool. What other questions do we got?
For a hash table, do you have to define the hash function every single time? And like, so I see the example that you gave with like the char code. Is that like the most simplest way to do it, or is that like a base case, or like, I guess I just don't understand them that much.
This is the simplest method that I could think of to produce something that technically is a hash. This is the simplest thing I could think of to make something that is a hash, just because it is deterministic. So it's going to give me the same answer every time I run this. And it's going to give me a number that is a valid array index for the data table underlying this hash table. So it does like check all the boxes and meets all my needs for a hashing function in this limited example. But this is not like a production grade hash function. I'd say that one way that you can judge hashing functions against each other is how likely they are to create hash collisions. A really sophisticated hash function should do that as rarely as possible, whereas a less sophisticated one will do that commonly. So here, I'm not exactly sure, but I would guess that there's like a 1 in 64 chance of getting a hash collision every time I add a new key to this hash, just because there's only 64 spaces in the array. And I'm assuming that all those numbers are equally likely, and I don't check for duplicates and don't have any like backup plan in that case. So this is a pretty unsophisticated hashing function.
Okay, thank you.
I hope that helps.
Yeah, and for hashing passwords, like you won't be writing hashing functions. There are libraries out there in all the different languages that like implement like pretty standard hashing functions for stuff like password hashing.
Oh yeah, that was the original part of your question, actually. So thanks for adding that, Adam. That's absolutely right. You're practically speaking never going to write your own hashing functions. Not for a hash table. You should rely on someone smarter than you to have already written a really fast and sophisticated hashing function. And especially that becomes more important when we talk about security, when we talk about password hashing. We don't want to reinvent the wheel, to save effort, but also just, I'm assuming that any authentication strategy, any password hashing function I come up with is not going to be as secure as the industry standard solutions that everybody else is already using. So just to avoid building a hackable application, we're going to use industry standard solutions. Now,
And those solutions have like had like thousands of people like looking over the code and finding issues, and it's been, bugs have been found and fixed and stuff. Yeah, hashing and like security stuff gets really, there's all these weird, tricky edge cases.
So that being said, in the password hashing lecture, I am going to show you once how you could manually hash a password to authenticate users in a web application, but we're only going to do that once just to drill in the concepts. And I'll make it clear at the time that that's generally considered a very bad idea and is like professionally irresponsible to do that like actually on the job. But it is cool to know how it works.
Yeah, data, I find data structures and algorithms to be really cool. And unfortunately, they're not like part of the day-to-day job of being a software engineer for most of us. But they come up in interviews, and the concepts definitely come up, I feel like in one way or another, like you see similar kind of things.
For sure. So I would actually say that this job is the only job I've had where I had to know data structures like to do the job. And that's just to teach it to you folks. Like any actual industry job, like I've never, like for the actual day-to-day work, never needed to know how to implement a hash table. This is just like trivia questions that people will ask you in interviews. And I guess if you were doing more low-level work, this could be relevant, but we're going to be doing higher level work generally, making web applications.
Yeah, same with me. Like the closest it's come, and I'm sure this is the same for you, Raphael, is like working with React and this library Redux that goes along with it. There are like some basic sort of data structure things that you don't even really use them. They're just sort of concepts in terms of how to organize data for like a single page app, a web app.
Yeah. That's looking ahead a little bit. So a lot of fun with React, a lot of fun with password hashing and authentication to come. If people have any more questions about today's lecture on data structures, I know we've gone over a little bit. We should probably release you to lunch before we just ramble forever. So last minute questions, anybody? Going once, going twice? Yes, no, okay. Thank you everybody so much for coming to my data structures lecture. I hope this was as much fun for you as it was for me.